Unit 5, Solutions, Lecture 4. We talked about titrations. Now we need to talk about millimoles, total and net ionic equations, and a problem that will summarize everything. But before we do that, we're going to kind of have a mental exercise by waking up this lecture with a problem that reflects on titrations. Here we are asked to calculate the volume of 3 molar nitric acid in milliliters needed to react with 5 grams of copper. So we have a 3 molar nitric acid solution here, and we want to know how much is going to be needed to react with 5 grams of this. We're asked to do it in milliliters. So I'm going to start with my 5 grams of copper and convert that to moles. 1 mole over 63.5 grams. Now I'm at moles of copper. I want to go to moles of nitric acid. And what is that ratio? What's that stoichiometric ratio? It is 8 to 3. You remember that. It's so easy now, isn't it? Times liters per 3 moles. Remember, it's 3 moles per liter on that nitric acid solution, but we need it in milliliters. Very simple, very straightforward, and something I hope that by now you are very comfortable with. So when we do this, and cancel moles also, we're going to come out with milliliters. And I have 70 milliliters of solution. Let's look a little more at millimoles. Now, you're probably going to think I'm going by my elbow to get to my ear, but I'm trying to make a point. Remember, molarity times liters is equal to molarity times liters. Of course, it's an identity. Well, a little algebra shows us that liters times moles per liter will equal moles. Of course, you see your liters cancel. Well, now based on that then, milliliters times moles per liter will equal millimoles. Milliliters times molarity will equal millimoles. Sure, watch. The liters cancel. So milliliters times moles per liter, which is molarity, is equal to millimoles. Or, if you will, milliliters times molarity is equal to millimoles written out. Therefore, molarity is, logically, what? Millimoles over milliliters. Millimoles, it's all just algebra that we're doing here. Just cancel your millis. Now your instructor may not like that too much, but oh, it works really rather well. Another way of saying this is to say that molarity is millimoles per milliliter. The millis cancel. Molarity is decimoles per deciliter. The decis cancel. Molarity is centimoles per centiliter. The centis cancel. And we could go on and on with this. But you get the idea. Now I want you to hang on to that thought, because we're going to introduce another important concept that is important in solution stoichiometry. And then we're going to wrap it all up with that wonderful problem I have been suggesting. Shift gears now and go back to the concept of metathetical reactions. And let's look particularly at the topic of total and net ionic equations. Let's consider a classic metathetical reaction that you've seen several times before. But let's look at this reaction occurring in an aqueous solution. It's the reaction of sodium hydroxide and hydrochloric acid to produce sodium chloride and water. But now let's look at it the way it actually is going on, or that we think is going on, as molecules and ions. Now the sodium hydroxide is a strong base. The hydrochloric acid is a strong acid. So we write the sodium hydroxide as ions and the hydrochloric acid as ions. And when they react, they produce sodium chloride and water. Well, sodium chloride is a soluble salt, so it is going to exist as ions in solution. But water, oh, that's a molecule. So it exists as a molecule, and it is the formation of that molecule that drives that reaction. Now look at this one. We have potassium chloride and silver nitrate producing a precipitate of silver chloride and potassium nitrate. Let's write it as ions and molecules. Potassium ions and chloride ions react with silver ions and nitrate ions. Why? Because both of those are soluble salts, so they exist as ions in solution. And when they react, they produce the insoluble silver chloride plus potassium ions and nitrate ions. Let's look at one more reaction, a little more interesting perhaps. Let's look at the reaction of ammonium hydroxide and nitrous acid, a weak base and a weak acid, producing ammonium nitrite and water. The ammonium hydroxide is a weak base, so we write it as molecule. The nitrous acid is a weak acid, so we write it as a molecule. The ammonium nitrite, that's a salt. It's a soluble salt, so what's it going to do? Yeah, it's going to exist as ions, ammonium ions, nitrite ions, and water molecules. Now, look folks, will the reactants, the ammonium hydroxide and the nitrous acid, before we even begin, will they conduct an electrical current significantly? The answer is no, they won't. They have so few ions in solution. Well, what about the products? Will they conduct an electrical current significantly? And the answer is, yeah, ammonium ions and nitrite ions certainly will. What we've been looking at so far are total ionic equations. And it's time now to convert and look at some net ionic equations. Net ionic equations show only those things that have changed. That's important. They show only the things that have changed. So here we have sodium ions and hydroxide ions and hydrogen ions and chloride ions reacting to produce sodium ions and chloride ions and water. Now what we need to do is cancel everything that did not change. Well, sodium ions didn't change, so we cancel those. Chloride ions didn't change, so we cancel those. The hydroxide ions did change, and the hydrogen ions did change. They formed water. So when we cancel the things that did not change, what's left? Hydroxide ions and hydrogen ions producing water. And that is the net ionic equation. That's what's actually happening predominantly in this reaction. Got the idea? Good, let's go on. Let's write some total and net ionic equations. Let's start with the reaction of sodium carbonate and hydrochloric acid solutions. First, I want you to write the molecular equation. As you get used to doing this, you may be able to bypass some of these steps. But let's start with writing the molecular equation. The molecular equation is sodium carbonate plus hydrochloric acid, producing sodium chloride, carbon dioxide, and water. Remember, this is the one that produces H2CO3 that you look for? Yeah. Now convert it to a total ionic equation. Well, the sodium carbonate is soluble, so it's going to exist as ions. The hydrochloric acid is a strong acid, so it likewise will exist as ions. The sodium chloride is soluble and is a salt, so it's going to exist as ions. Carbon dioxide is going to come off as a gas, and the water molecule is going to be formed. Now let's cancel that which doesn't change. So we cancel sodium ions, and we cancel chloride ions, and look, everything else changes. So now we write the net ionic equation, which happens to be the reaction of the carbonate radical with the hydrogen ion producing carbon dioxide and water. Are you getting the idea? Let's try this one. Let's write total and net ionic equations for the reaction of lead nitrate, plumbous nitrate, and potassium iodide. Now here is the whole thing right here. We have lead ions and nitrate ions and potassium ions and iodide ions, giving us a precipitate of lead iodide and leaving potassium ions and nitrate ions. Now, you stop for a minute and write the net ionic equation. Did you get this? The plumbous ions plus the iodide ions giving us plumbous iodide. No, I know it's not balanced. You can balance that or just leave it right now, whichever you wish. But I have a question to ask you. What are these? What are those things? They weren't part of the net ionic equation. They were part of the total equation, the part of the total equation that wasn't used. But what are they? Well, they are called spectator ions. I guess if we were going to give them a modern term, we would call them couch potatoes because they kind of sit around doing nothing. Except, I suppose if you put electrodes in there, they would conduct an electrical current. Well, let's look at some more total and net ionic equations. Let's look at the reaction of ammonium hydroxide and aluminum chloride solutions. Now, when we write this out as the total equation, how do we write the ammonium hydroxide? It's a weak base. And how do we write the aluminum chloride? It's a soluble salt. So we write these as ammonium hydroxide molecules plus aluminum ions and chloride ions. And they react to produce ammonium ions and chloride ions and aluminum hydroxide precipitate. Now we have that reaction. Let's look at the net ionic equation. What's the spectator ion? The spectator ion is the chloride ion. It's the only one that doesn't change. And this only has one spectator ion, and that happens to be the chloride. So the net ionic equation then is what's left? Ammonium hydroxide plus aluminum ion, producing ammonium ion and aluminum hydroxide precipitate. And folks, it doesn't matter if we use aluminum chloride or aluminum nitrate or aluminum bromide or aluminum whatever. The net reaction is going to be the same here. Let me prove that to you by using this reaction. Let's look at the reaction of ammonium hydroxide and aluminum bromide solutions. Well, ammonium hydroxide is a weak base. Aluminum bromide is a soluble salt. So it looks like it's ammonium hydroxide as a molecule, aluminum ions and bromide ions written as ions, yes. And when they react, it produces ammonium ions and bromide ions and aluminum hydroxide precipitate. Now, what's the spectator ion? Well, it's the bromide ion. So if we take that out, the net ionic equation is identical to the one that occurred when we used the chloride. Try your hand at this by using the reaction of nitrous acid and barium hydroxide solutions. Stop the video, do the total ionic equation and do the net ionic equation, and then click back on this and I will show you what I got. The total ionic equation is nitrous acid, written as a molecule because it's a weak acid, plus barium ions and hydroxide ions, written as ions because they are from a strong base, reacting in an acid-base reaction to produce the salt barium nitrite, barium ions and nitrite ions, and they produced water as a molecule. The spectator ions are what? Well, let's see. Here's barium ion, and I believe that's the only spectator ion. So the net reaction is the weak acid nitrous acid plus hydroxide ions producing nitrite ions and water. The barium doesn't show up. We could have used sodium hydroxide in place of that. We could have used calcium hydroxide in place of that, barium hydroxide, and we would have gotten the same net ionic equation. Now it's time for us to combine a lot of the things that we've been talking about. And this is just the problem to do that. We have 150 milliliters of a 0.1 molar lead 2 nitrate solution that has been added to 90 milliliters of a 0.140 molar potassium iodide solution. And we need to find the concentration of all of the ions that remain and the mass of the precipitate that is formed. All right, how do we go about this? Well, first thing we do is write the total ionic equation. So here it is. It's the plumbous ion plus the nitrate ion. And notice here, folks, we have 2 nitrates right here for every single one of the leads. We have the potassium ion and the iodide ion. And it's going to produce the precipitate of potassium iodide, and it's going to leave of lead iodide, and it's going to leave potassium iodide and nitrate ion in solution. All right. Let's start by noting all of the quantities of materials we have. So for the lead nitrate, we have 150 milliliters of a 0.100 molar solution. And for the potassium iodide, we have 90 milliliters of a 0.14 molar solution. Now, it's important that you have that always there in your view, because you're going to use that to calculate all of the rest of this problem. Let's start out by saying how many millimoles of each is initially present. How many millimoles of each ion or molecule is initially present? Well, let's start with the lead nitrate. We have 150 milliliters of a 0.10 molar lead nitrate solution, or plumbous nitrate. Now remember right here, remember how your cancellations go? You have milliliters here and you have moles per liter here. So liters are going to cancel liters and leave you with millimoles. Remember that. It's a neat trick. That means then when we multiply that 150 milliliters times 0.100 molar solution, we have 15 millimoles of lead ion. But how much nitrate do we have? Well, notice we have a 2:1 ratio of nitrate to lead. So for that, we have 30 millimoles of nitrate ion. Get it? Okay, let's go to the potassium iodide. Now, the potassium iodide is a 1:1 ratio. The 2's in front of the potassium right here and the iodine are strictly there to balance the equation. They have nothing to do with the relationship that exists between the potassium and the iodine. So we have 90 milliliters of a 0.140 molar solution. Multiply that and you find that you have 12.6 millimoles of potassium ion and the same amount of iodide ion, 12.6 millimoles of iodide ion. Now you know the amount of each material that you start out with. Folks, when you look at this, what you're dealing with is a limiting reagent problem. So ask yourself, what's going to react? Well, what's going to react is the lead right here, the plumbous ion, is going to react with the iodide ion and form this precipitate right here. So we have the lead ion plus the iodide ion forming the precipitate of PbI2. Nothing else is reacting in this problem. How much of each ion is going to remain after the reaction occurs? Well, let's start with the plumbous ion, the lead ion. We have 15 millimoles of that. How much reacted? Well, we take 12.6 millimoles of the ion times 1/2. Now, why did I use that? I use that because the plumbous ion is reacting right here with the iodide ion. And it's 2 iodide ions for every plumbous ion. So the iodide ion is going to be our limiting reagent. Now, if you don't see that, then go back and treat it the way you would limiting reagent problems and figure it out. But the fact is, when you run this calculation, you're going to see that you have 6.3 millimoles of lead iodide, plumbous iodide being produced. Well, the 6.3 millimoles of plumbous iodide comes from the fact that you have 12.6 millimoles of iodide ion. And if you're going to produce 6.3 millimoles of plumbous iodide, and you subtract 6.3 millimoles of plumbous ion from the 15 millimoles that you have, this tells you you have remaining 8.7 millimoles of plumbous ion running around in the solution. Okay. How much iodide do we have? Well, we used up 12.6 millimoles of iodide ion, which is all we had to start with, so we don't have any iodide ion at all that is left. Here now we have 8.7 millimoles of plumbous ion. Well, what about nitrate ion? How much of that do we have? We have 30 millimoles of that. Why? Because it didn't react. It's a spectator ion. Well, how about the potassium ion? We have 12.6 millimoles of potassium ion also. Why? Because it too is spectator. So none of it reacted. We have none of the iodide ion left. All right, let's look at a summary of this. How much of everything do we have? Well, here's what we have. For the plumbous ion, we have 8.7 millimoles left. For the nitrate ion, we have 30 millimoles left. For the potassium ion, we have 12.6 millimoles. And for the iodide ion, we have none of it left. All right, getting the idea? Now let's see if we've done this correctly. And there's a trick, and that is look at the number of millimoles of positive and negative charges. Let's add them up. Well, we have 8.7 millimoles of plumbous ion right here at +2 charge each. Yeah, and we have 12.6 millimoles of potassium ion right here at +1 charge. I tell you what, you add that up, and you're going to find that the total charge, that the total concentration of positive charges is 30, or the total number of millimoles of positive charges is 30 millimoles. Well, what about the negative charges? Folks, the negative charges only come from the nitrate, and that is also 30 millimoles. Your equation was balanced to begin with. Charges had to be balanced. You've precipitated out the material that is insoluble, and what you have left are charged entities and possibly some molecules, but the positive and negative charges have to be equal, and they are. That's your first clue that you've done this right. Now, we wanted the concentration. So let's convert from millimoles to molarity. Remember how to do that? Do you remember what you need? What's the total volume of the solution, theoretically? Well, the total volume should be 90 milliliters plus 150 milliliters to give us about 240 milliliters of solution. Now, do you remember how to convert from millimoles to molarity? Sure, you remember. You take your millimoles and you divide it by your milliliters. So let's start with the lead. The plumbous ion is 8.7 millimoles divided by 240 milliliters gives us 0.036 molar plumbous ion. So the solution is 0.036 molar in plumbous ion. So let's put it over here and record it. There we go. Now let's see. The 30 millimoles of nitrate divided by 240 milliliters is going to give us 0.083 molar in nitrate. So we'll put that here. And let's see. We have, for the potassium ion, we have 12.6 millimoles of potassium ion over 240 milliliters. That gives us 0.053 molar potassium ion. Put that here. And what about your iodide? Of course, if you put 0 millimoles over 240 milliliters, you get nothing, right? So there's that. Now we have the concentrations of all of these things that remain. Now let's find the mass of lead iodide, plumbous iodide. How do we do this? Well, let's see. How much plumbous iodide did we form? Well, we had 6.3 millimoles of the plumbous ion used, and 12.6 millimoles of the iodide, but that could only go with the plumbous ion, so I believe that we produced 6.3 millimoles of plumbous iodide. And we want the mass of it, so 6.3 millimoles times 1 mole over 10 to the third millimoles times 461 grams per mole tells me that we produced 2.9 grams of potassium iodide solid. Folks, you may have to go back and walk through this a couple of times, and if necessary, do so, but it is a great problem. In this unit, we talked about a number of things. After a brief introduction, we talked about electrolytes, strong electrolytes, weak electrolytes, and non-electrolytes. We talked about metathetical reactions, which in our case we're talking about double replacement reactions, and the factors that drove these reactions, and you recall there are 3 of them. We talked about concentration in terms of percent. Percent that was mass, percent that was mass volume, and percent that was volume. And we spent a lot of time dealing with molarity. We very briefly talked about pH and wrapped up the whole unit on stoichiometry. A better way to teach and learn chemistry.